Thank you for coming here today. During this session, we will talk about seamless mobile real-time communication with WebRTC and how to use it in a mobile app, of course. But before that, let me introduce myself. If you don't know me, I'm Renaud Mathieu. I'm a freelance based in Paris, member of the Paris Android user group, and of course, proud of being here with you today. You hear me? Why this talk? I had the opportunity to discover the WebRTC standard during a freelance mission for a client in video games, and more specifically in cloud gaming. Last year, during this mission, I was able to set up a Compose multi-platform project to deploy a cloud gaming solution based on WebRTC. So basically, it was a remote controller, mobile app remote controller. So you speak with it, with the video game in the cloud gaming, with WebRTC. So this is going to be a feedback of experience. And I was able to discover things that I will share with you today. So WebRTC, Web Real-Time Communication. It's a technology that enables real-time communication capabilities directly into web browsers or mobile applications. Its development and also the adoption mark significant milestone in the evolution, of course, of web communication language and technologies. With WebRTC, the peers, they can stream video, audio, or even arbitrary binary data. So you see binary data for cloud gaming is perfect. But before starting more deep, let's take a small step back and have a look on what's the story behind WebRTC. So, 2009, long time ago, the concept of real-time communication in browser without the need for plugins started gaining traction around 2009, 2010, and Google played a significant role in this period. They acquired the global IP solution, that name was Gips, in May 2010, and this was a company that was famous for developing an high-quality voice and video processing software. In May 2011, Google announced the WebRTC project and open-sourced its key components. The move aimed to standardize the technology and make it freely available to developers and browser vendors. Then, the World Wide Web Consortium, the W3C, and the Internet Engineering Task Force, the IETF, began working on standardizing the API and the protocols. The W3C focused on the JavaScript API, while the IETF worked on the underlying protocols and the data format. 2012, Mozilla and Google started implementing the WebRTC in their browser, Firefox, Chrome. This period marked the beginning of practical experimentations and usage of WebRTC in a real-world applications. 2014, WebRTC began gaining traction in the industry. Various startups and established companies as well integrate WebRTC into their product for video conferencing, also for file sharing and real-time data exchange. In 2015, the technology matured with improved stability and performance, and we discovered services like Appear.in, that is known as Whereby, and other video conferencing tools that showcases the WebRTC's potential and in consumer and enterprise applications. But it's only in 2018, so almost 10 years later, that the W3C officially published the WebRTC 1.0 standard that made it a significant milestone, of course, in the development of WebRTC. By this time, the WebRTC had seen widespread adoption in various domains, also including telehealth, online education, customer support, social media, and video gaming. 2020 until now. So the COVID pandemic accelerated the adoption of WebRTC as the demand for remote communication tool skyrocketed. platform like Zoom, Google Meet, Microsoft Teams, so a massive usage, and many of which leverage WebRTC for their web-based offerings because of remote work. Okay, that was part of the history. I think it's nice to have this in mind because it has been there for years, and also with the COVID pandemic, we can see that actually it skyrocketed and it's still here and useful nowadays. So you might ask, how is WebRTC architectured? So let's dig a bit into the standard and the way things are working with WebRTC. Let's take the mesh architecture. In a mesh architecture, all participants are directly connected to all other participants. So, in a graph theory, a graph where each node connected to every other node is called, in the graph theory, a complete graph. For a complete graph with n, which is n nodes, the number of edge connections that you can see here, the arrows, can be calculating with the formula of n times n minus 1 divided by 2. So it's very huge if you put a lot of nodes. So this solution, it has some advantages. It's easier to set up with a low operation cost, but it requires a high bandwidth for each node, and it's also, as we mentioned before, non-scalable for many participants inside a video conference, for example. Another architecture, the multi-point conference unit. So basically, there is a server, and the client A speaks to the server, and the server will filter and send to client B and client C the messages. Oh, sorry, went a bit too far. Yeah. This solution requires high computational cost for decoding and coding the stream. It also brings high latency at large scale, and the server is a point of failure and needs a big bandwidth to work with many participants. So this is the multi-point conference unit architecture. Sorry. So let's look at how WebRTC works. You have a server. What we are going to call it later is the signaling server. We have a client A and a client B. So the client A creates an offer and sends it to the signaling server. The signaling server relays it to the client B. Client B receives the offer. Then the client B creates an answer and sends it back to the signaling server. The signaling server relays it to the client A. Client A has received the answer. So after that, we have the ICE candidate exchange. We will see a bit later what is it. And sending to the signaling server. And both of them are gathering all their ICE candidates together. And once it's done, through the relay server, once it's done, they establish a peer connection together. To my opinion, what we have seen here, the process of establishing the WebRTC connection between two peers can be divided into two major phases. What we have seen here, the signaling phase, the phase that involves the exchange of connection information necessary for peers to connect directly, basically sharing your ID. This phase is not handled by the WebRTC itself. Instead, it requires an external signaling server or any other mechanism. It's not part of the standard. The second phase, the peer-to-peer connection phase, this phase actually involves the actual establishment of the peer connection and also enabling media, data to flow directly between the peers. So 2 steps. Let's have a look. I mentioned ICU. What is it? It's interactive connectivity establishment. It's a technique that combines the stun and the turn servers to discover and establish the best connection paths between WebRTC clients. Basically, it's how we enable real-time communication even in challenging network environments. The stun server is a protocol that is used to discover the public IP address and port of a client. You can use by default stun server from Google, and for free you can discover the public IP address and port of any client. The turn server, it actually acts as an intermediaries with direct peer-to-peer connection, and when they are not able to connect in restrictive network configuration. So basically, they relay media streams between clients and ensuring the reliable communication. So let's have a look, a summary of the WebRTC architecture. I try to draw it like this. So, of course, you can see the NAT here, the network address translation. That's just the method of mapping an IP address space into another. So not changing another address, but actually changing the header inside IP headers of packets while they are in transit. So this is the NAT. So you can see there is a signaling server, turn server, also stun server to establish the connection between client A and client B. Some information that worth mentioning that we have seen before. So the WebRTC specification, it includes API for communicating with an ICE server. The signaling component is not part of the standard. The WebRTC, it's worth mentioning that transmit data using UDP, the user datagram protocol. So UDP is connectionless, which means that there is no establishment of a formal connection between before data transmission. So each UDP packet is independent and can be sent to the destination without any prior setup. It has a minimal overhead to the transport. So basically, there is no acknowledgement, so you can lose packets. It doesn't provide control mechanism like TCP. With UDP, cannot manage error recovery or acknowledgement of received data. So this increases the risk of data loss. One thing that's worth mentioning is this link. You will be, how do you say that? Yesterday, I ran some tests going to this, and actually you can see all the WebRTC connection through your web browser. And for fun, I just opened LinkedIn, and you see that they are establishing a data channel, and so basically it can be useful for the feed. And you can see that many companies are actually using WebRTC, but for LinkedIn, you don't know that, but they are opening this. And if you want, go to this link. It works also for Arc browser, and you will be surprised by the things that are going on when you're visiting websites. Okay, so we have previously seen that the signaling server is needed in order for two peers to share how they should connect together. Usually, this is solved through a regular HTTP-based web API or a REST API service or any RPC mechanism, where the web application can relay the necessary information before the peer connection is initiated. Before that, I've shown you my simple diagram. This is the real one. Sorry, it's a bit blurry. But well, let's have a quick look on the sequences diagram to establish a connection between two clients. This diagram actually takes the full sequence. What you can see here before, it's initialized the WebRTC. We set some local description, making sure that we are creating the offer with the local description. So basically, who I am, please build my ID, send an offer, the signaling server relays the offer, we receive the offer. Okay, we got this offer, so from this offer we can create an answer. So this is also my ID. Send the local description, send it back, read it back, receive the answer. So now, first phase, and second phase, okay, gather my ACE candidate, send my ACE candidate. So you can see this is asynchronous. Relay my ACE candidate, receive all the ACE candidate, gather the ACE candidate and send it back, relay the server, receive ACE candidate, add it. And with this, once this is complete, we actually set up a peer connection between client A and client B. After that, we don't need the signaling server anymore. It's just here for setting the things up. Once it's connected, we don't need it anymore. Okay, so we are Kotlin engineers, since we are all doing Android. We can use Ktor for writing our signaling server. So let's write it together, if you don't mind. Because creating a signaling server for WebRTC in Ktor involves setting up a server that can handle the exchange of SDP, the session description protocol that we've seen, some messages, and also share the ICE candidates between peers. So, for those who don't know Ktor, just bear in mind that I wrote some articles. So if you want to put your hands on Ktor, I think it's a great tool. And since we're Kotlin engineers, works fine. In any case, so what we're going to do, I will bypass this step because it takes great old time to set up. So we're going to go to start Ktor.io and use a WebSocket, because WebSocket in this case is fine because we have to exchange quickly information between client A, client B with the signaling server. Feedback from the field, never send string like this. I think it's a better thing to wrap everything into one packet, for example. What I called here is WS, like WebSocket packet, to make the distinction. And what I think is good is you put your messages, am I an answer, am I an offer, etc., and your data here, because it will be easier. You could also put timestamp, etc. So it's always great to consider wrapping everything before starting. And the WS messages could be ICE candidates, ICE server, initialization, and so on for offer. We don't need more than this, actually, to establish the connection. Okay, so let's have a bit of Ktor things. The tricky thing is that there is client A going to signaling server. We have to know who is connected to my server. So for that, Ktor is very simple. We just put an atomic ID, and when there is a session in the default WebSocket, we just know that it's client 0, client 1, client 2. So let's make it very simple in this case. With Ktor, setting up a WebSocket is very simple as well. You just install the plugin WebSocket. This is from the documentation. What we need is just use Kotlin X WebSocket serialization converter for JSON, because what we would like to do is wrap everything in objects so we can manipulate them easily. And then we just have our connection. So once someone is connected, we just put it in the pool of connections. So now we just use the routing. This is where we could create the WebSocket, and we put connect here. So there is many ways to do it in Ktor. I put the more idiomatic way with a for loop. There is flow, of course. There is a lot of good API, but I think this one is the easiest to understand. We just had the connection. We also require to make sure that everything works with the try-catch. And then this is where it goes. So basically, since we've wrapped every packet with a message, we can distinguish what I've received to actually relay the good information. So let's do something here. What we need to think about, this is this part. Because the client A sends to the server some information, the server doesn't want to send back to client A. So we have to make sure we send to all the other ones. So we are not going to ping-pong to the client. So we filter. So this is the way of stupidly, because I put a name. So filter that I'm not the one that's received and I'm sending back the data. So that are the two things that are happening here. We don't want to send any data to the one that sent us something. And we are going to cheat a bit here, since we can send directly the data here, thanks to all the setup that is going to happen in the next slide, which is, you know what? It's very easy to set up a peer connection in web. I'm not a web developer. This looks like, oh my God, this is HTML, etc. But what I told you before is that it's part of a standard. So they made us sure that there is no plugin involved in web browser nowadays. So this is very easy, even for me, which I'm not a web developer, to set up a peer connection in web. So what I did here, so basically, sorry, it's a little bit of HTML and JavaScript, but I'm sure you're fine with this. There's the local video, the remote video, and this is my local server here, the WebSocket, putting my server. So this is very easy. Sorry, I'm going to start my WebSocket and my signaling server in this local host for convenience, because you don't know what the Wi-Fi is in conferences. Local peer connection, the remote, before displaying. And also, we just pass the value. And what is great is that everything is already handled. You see, a Navigator media device, you get it out of the box. So the local peer connection out of the box, everything is out of the box. So we just have to follow the rules that, okay, this is my offer, this is my answer, this is my ICE candidates. And then, so you see there is not so many code, but what I can do is just showcase you how we can going to set up a signaling server and then establish a connection between two peers. So, as you can see here, I didn't put the while loop here, I just put the consume each, which is another API, but it's not a problem for this, and just the filtering, and then I'm sending the frame. So let's start. Okay, and let's open two things I created. You will see that. Oh, it's big, very big, sorry. Oh, so this is my local video. And another window with a remote one. And here, so it's two different tabs. And you can see behind that actually we exchange. See, the offer was here, then we got the answer, so we read everything here. And it's just the two HTML files that I've showcased you, plus the 5 lines of code in the Kata server. And where am I? And here you can see there is the local and the remote. So you're going to see, hey, you're cheating, it's both local. No, actually, if you look a bit deeper, you will see that I didn't correctly set up some media streams. So in this side, the quality of the video is a bit, I mean, in local it's better than in the remote video. So if you look, but it's very hard to say, but you will see in Android, I put some stuff after that to make it worse. So that's it. Signaling server, not part of the standard, but actually WebSocket, and that's fine. So now let's go to the next part. So let me close this. Let's play Android. Now we have our signaling server. Let's look on how to use it on Android. You probably heard of third-party SDK allowing you to easily set up a video conferences, get stream. Maybe you have heard of one famous Android developer called Jae Wong in South Korea. He's a huge contributor, you know him. So he's working on this. So basically what they are doing is wrapping the WebRTC standard into an SDK that makes us developer, actually it's faster for us to set up a video conference app. They are not the only one around. There is also LiveKit. And LiveKit, what they did, they are actively maintaining WebRTC SDK for Android. So basically, Google is releasing SDK for iOS, for Android, for any other platform. And what LiveKit is doing is that they are forking and making sure they implement the standard in WebRTC SDK. So as an Android developer, we could directly use libWebRTC from Google, or this fork from LiveKit, or directly LiveKit, but it's paid. The benefit of using the SDK is that it makes everything very simpler. Okay, so that's under the hood. In a client-server communication architecture, we have state machines and asynchronous calls. And there are two different paradigms for managing interaction and workflows. So state machine is best suited for a scenario where the workflow is complex, involves multiple states, and requires clear state transitions. In my personal experience, dealing with the peer connection through WebRTC, also a signaling server with a WebSocket, and sometimes, and you will see most of the times, other things depending on your app, it will be easier to deal with a state machine. Asynchronous, as you have seen in the diagram sequence before, can be tricky because there is sometimes callback, but sometimes asynchronous. So it's better to know that, okay, there is phases. There is the signaling phases. So let's be in a state where I'm into the WebSocket part, because it's the connection with the WebSocket from the signaling server. And then I'm into a WebRTC connection, established connection, where I can send actually the video, the audio, or even data, and then do something like mute this participant, hang up the connection, the call, etc., etc. So, in a classical Android architecture, I would recommend this. WebSocket data source, it's in charge of communication to the signaling server, open and close the connection with the signaling server, and also can be used to maintain, we have seen that in Cater, the ping connection to ensure that the connection is always open between my client, my Android application, and the signaling server. And also, bear in mind that can be useful since it's a server and it's handled on your side, that you can use to inject some specific commands from your signaling server. I don't know why, like analytics or don't know, but you can still send things there. Then you have the WebRTC data source in charge of the very useful object that we're going to use in WebRTC called the peer connection object. That's also in charge of creating, receiving the offer, the answer, and also add the highest candidates and negotiate the RTC configuration. So, then, we combine the flow from both data sources and produce the state that our app will use. Are we paired? Are we connected? Are we in error? All the state that we're going to manage is going to go through this connection repository. And then, used by our UI, we can inject events, because the UI can inject events like mute this person or hang up, to produce a new connection state or retrieve some commands from the peer or from the signaling server when the server from the signaling server is actually sending you some information. So, let's have a look on the WebSocket data source. We used Cater server to build our signaling server. So why not using Cater client with our Android app? So what we're going to do, we are going to open the WebSocket in this case with the connection. Here I put the real protocol WS, but it's better to put a secured one. So it was for my test. Then there is just how to manage the session. So it's not so tricky here. Then send messages, very useful. How am I going to send serialized packets and how are going to receive this serialized WS packet? The WebRTC data source, so it uses the library WebRTC under the hood. So we have to have a peer connection. In the standard, a data channel is something apart. So you have audio track, you have video track, but there is data channel on the side. So we need a connection job, supervisor job is fine, with a coroutine scope, Then you gather a stream from all the ICE candidates, and the peer connection state makes you sure that in which state you are. And then, for my purpose here, because it was for video gaming, I created a data channel. You can put whatever ID, whatever value you want here. But what is important is that put that in state, and then you will see later that you know our state from the WebRTC connection. Then it's fully WebRTC standard. How to create an offer, so we have seen that before. The local description has to be set up to create this ID. How to create an answer, how to create the RTC configuration. So here you will see that there is the ICE server that needs to be created. So it's all set up. And for RTC configuration, well, I use the stun server. Also, I think Twilio is, from what I heard, that Twilio's stun server is a bit faster, but that's people from backend, I didn't check. But you can find it online. Okay, so connection repository. This is where all the magic comes. It's here, the combine. So we have the WebRTC, the WebSocket. We have the peer connection state that is produced thanks to a WebRTC data source, and we have the packet that is received from the WebSocket data source. So we have just a coroutine scope, the two data source, and the connection information that can be shared from your UI to establish the connection to the signaling server. And then, since I've said that it's better to wrap everything in packet, but we benefit from it from the when. So if it's an error, this is what I'm going to do. And then, if it's another one, then I can decode the ICE server, set them, the RTC configuration. And then here, you can see, it's all the asynchronous things that we have to do when there is nice configuration happening. So big win with the combine. Makes life easier. You don't have to deal with asynchronous things. We just get our state, and that works fine. That works fine. Sorry. And then what I'm exposing to my view model is: am I connecting, or am I already connected, disconnected, failure, in connecting? So the UI know what has to be done, like a loader, or everything is set up. So now you can play the video or send data. Don't forget to close everything. And I put that in a state, so a shell flow, and created also a new pair state, but just up to you to set up these things. The ICE server, here, it's a bit tricky because we have to have the ICE candidates, and also it's stuff, I must admit that I have no idea what is it. SDP mainline index, SDP myID. It's part of the standard, so sorry. I didn't read the documentation, but I just passed them and it works, so sorry. So, for Android, you have seen that what we have done so far. We have created a signaling server using Cater server, a few lines of code, just sending raw data. On the Android side, what we have done is handle the signaling server with the WebSocket on the side. Then with the WebRTC, we are using the protocols, the SDK from Google, the libWebRTC SDK, and we are using the objects. Then we create a repository that combines this and expose a state, and then the view model can actually have, am I paired, am I connected, is it a new established connection, or is there a failure? And that works. But you all wonder, okay, that's fine, Android. What we have done so far, we could have done it 2 years ago, same code, except for the flow. How about multi-platform? So, you are familiar with this graph. So we have the server for common multi-platform. We have Android, iOS, desktop, web. So there is Alex Shepiliev. He's an Ukrainian guy. He did a great job in bringing WebRTC to multi-platform. Since WebRTC is a standard, we can take the iOS SDK, the Android SDK, the WebRTC adapters from for example, JS. Then we wrap everything into a Kotlin multi-platform library. And there is room for improvement in library or debugging, so you're free to participate if you like. But basically, it's just building a Kotlin multi-platform library out of standards that are actually calling the same method since it's a standard. So creating an offer will be the same method in iOS and Android, so we can wrap everything. And for video, what is funny is that we expect a video. So video stream track is actually an object that we are going to expose to all our multi-platform clients. The modifier, the audio same. And then this is the actual for Android. So we have the Surface View renderer that you might be aware of. So it's an Android view for now. What has done, by the way, Stream.io is that they've wrapped everything into a Compose library SDK. So that's one of the benefits of GetStream. And I think LiveKit did the same. So it's easier. So you don't have to do the Android view with their SDK. For what is that? For iOS, a UIKit view with a factory, and then we benefit from this RTCMTL video view that's actually from the UIKit part exposition of the WebRTC implementation in iOS. And then we set everything. And that's the only lines of code for this. And this is what I'm going to show you a bit. This is WASM. So basically what we're going to do, since it's a standard in web, we're just going to use the element video as a HTML video element and put the stream as the media provider. And then we can display the video. So let's have a small demo for this. So this is what I was talking about, the Android. Also, there is some lifecycle involved because when you go background, etc. This is the one for iOS and the one for WebM. So if I go to Android, so this is a Kotlin multi-platform project, a sample for this. My device is in this side. Can you see it well here? It's going to be launching. It's a lot of time. It seems that okay. It's just a bit laggy. Wow, it's very laggy. Maybe I will kill this one. Sorry, my emulator seems to be laggy. Okay, so we have the local, we have the remote, so we can start. And, oh, sorry, it's a bit laggy. So in the meantime, while it's taking care of, I have the WASM here. So it just composed WASM brother here. You can see it now. So it's a bit laggy, sorry. But you might see that the quality is bad. I put some explicitly some bad media. So you can see on the remote side, the quality of the video is not good. On purpose. Oh, sorry, it's yeah. It's a bit laggy. It's not laggy, it's my simulator. Don't worry. And then with the WebAssembly, so let's do it because it's the future, right? And you see, it's the same buttons. It's Material 3. Let me kill this one because it takes... wow. Ouais, bon, sorry. Anyway, this is local and the call. You can see the quality here is a bit different. So this is again WebAssembly. 1 minute? Okay, so you have to hurry. Go straight to the conclusion because the conclusion is very funny to my opinion. What is next? What is next is that we have Selective forwarding unit, client A, client B. The problem is that it doesn't scale, right? Client A, client B. So what we are going to do, and what people are doing in companies, they put a server, and actually what it's going to do is just act as we establish the peer connection between client A and server, client C and server. So this is how it's going to be handled. This way, it actually scales. So this is the architecture that they are using when you are in a multi-conference room, for example, the selective forwarding unit. It brings many potential. It's called an SFU as well. They don't process the media, but rather route it around, and as such, they consume considerably less CPU than the multi-point alternative, and their performance relies heavily on the network throughput. With that, they can do many things like simulcast that involve sending multiple video streams, also protocol converter, and what you can see sometimes you see that there's pixels because your fellow colleague, his network is bad, so there is huge pixel. So with this unit, it knows that the connection is bad, so maybe we can encode the value a bit so it can work for him and require less bandwidth. What is next? Why actually WebRTC company exists? The business increased with the COVID. WebRTC offers powerful foundation for real-time communication, but it has its limitation. This is where WebRTC companies step in. Scalability and performance, because it requires some development effort. Security, of course, and compliance, because we implement robust security measures and also data privacy. By default, the standard, the exchange of offer answer is normally supposed to be good in terms of security. It's also brings us some benefits of customization, and it's actually easier to set up. This is all the company that are actually involved in WebRTC. There is some use case like EdTech with the virtual classroom, telehealth, HR tech, fitness, social, gaming, event, dating, for example. What is next for the selective year? So, as we look to the future, the integration of AI and ML technology in WebRTC, this is set to revolutionize a bit the user experience. With the innovation, of real-time language translation, noise suppression, AI-driven video enhancement, the possibilities are endless. And you have seen in the selective unit, this is where they put their value. So I hope that with that, I've shown you that today, as Kotlin developers, we have the tools, because I didn't show iOS because I forgot my iPhone, sorry, but it works fine. Today, as Kotlin developers, we have the tools, capabilities to achieve incredible things across multiple platforms, whether it's WebAssembly, iOS, backend, or Android. Our skills are more relevant than ever, to my opinion, and this is rapidly an evolving landscape with the AI and all the opportunities that it brings to us because we have the tools. Sorry if I'm a bit late. Thank you very much for listening.